orbital hybridization, a key topic of paramount importance in physical chemistry. Today, I'll cover 3 important subtopics in orbital hybridization at the A level or pre-university level, using simple language and intuitive animations. Watch until the end, and I'm sure you score 100 marks in your A-level examination.
Oh yeah!
Like what I did.
Wow!
Today's topic has 3 subtopics. Subtopic 1. What are the differences between SP, SP2 and SP3 hybridization modes? Subtopic 2. How to find the hybridization mode of C, N, and O in a molecule. Subtopic 3. What is the relationship between hybridization mode and molecular geometry? Let's get started. We will use carbon as an example. Before that, we need to know the electron configuration of carbon. It is 1s2, 2s2, 2p2. This is the diagram for the ground state of the electron configuration. The carbon atom has to undergo 2 stages before it can form covalent bonding with another atom. Step 1. Excitation of the electrons. Step 2. Hybridization of the atomic orbitals. During excitation, 1 2s electron would gain energy and rise to the 2pz orbitals. The next step is hybridization. Hybridization is the intermixing of atomic orbitals to form new hybrid orbitals in order to form a covalent bonding with another atom. During hybridization, the atomic orbitals in the valence shell would reconfigure themselves to get ready to form covalent bonds with another atom. In carbon, there are only 3 types of hybridization possible, namely sp, sp2, and sp3. In sp hybridization, the 2s orbital and the 2px orbital combine to generate new orbitals. Let's look at this animation. Combine, mix, and regenerate the orbitals. It's important to note that 2 orbitals combined must generate 2 new orbitals, and each new orbital is named an sp orbital. In sp2 hybridization, the 2s orbital, 2px, and 2py orbitals combine to generate new orbitals. Let's look at this animation. Combine, mix, and regenerate the orbitals. It's important to note that 3 orbitals combined must generate 3 new orbitals, and each new orbital is named an sp2 orbital. In sp3 hybridization, the 2s orbital, 2px, 2py, and 2pz orbitals combine to generate new orbitals. Let's look at this animation. Combine, mix, and regenerate the orbitals. It's important to note that 4 orbitals combined must generate 4 new orbitals, and each new orbital is named an sp3 orbital. The number of hybrid orbitals generated by each type of hybridization is the most important factor to determine the hybridization. sp hybridization generates 2 new orbitals. sp2 hybridization generates 3 new orbitals, and sp3 hybridization generates 4 new orbitals. How is my animation on orbital hybridization? Do you find it intuitive, engaging, and easy to understand? If you find it helpful, I hope you can show your support by hitting the like and share buttons. Making such an animated education video is not easy. It takes a lot of time, effort, patience, and motivation, and your support means a lot to me.
Let's continue.
How to find the hybridization mode of C atom.
These 2 C atoms are equivalent, so they have the same hybridization mode. The number of sigma bond is 4. The number of hybrid orbitals needed is 4, same with the number of sigma bonds. From this previous slide, we can recall that the hybridization mode that provides 4 hybrid orbitals is sp3. So the hybridization mode is sp3. What is the hybridization mode of the H atom? Remember, hydrogen atom has only 1 atomic orbital, 1s. Therefore, it cannot undergo hybridization. For ethene, the 2 C atoms are also equivalent. The number of sigma bond is 3. Remember that in a double or triple bond, only 1 is sigma bond, and the rest are pi bonds. The number of orbitals needed is 3. The hybridization mode that provides exactly 3 hybrid orbitals is sp2. For ethyne, the number of sigma bond is 2. The number of hybrid orbitals needed must be the same, so it is also 2. And the hybridization mode that provides exactly 2, no more, no less, is none other than sp. So the hybridization mode is sp.
How to find the hybridization mode of an atom?
For ammonia, the number of sigma bond is 3. The number of lone pair is 1. The number of hybrid orbitals needed is the sum of these two, 3 plus 1, which is equal to 4. Recall from this slide, which is valid for all elements, the hybridization mode should be sp3. In hydrogen cyanide, for the N atom, the number of sigma bond is 1. The number of lone pair is 1. The number of hybrid orbitals needed is 1 plus 1, which is 2. And the hybridization mode that provides exactly 2 hybrid orbitals, no more, no less, is sp. For the C atom, the number of sigma bond is 2. The number of lone pair is 0. The number of hybrid orbitals needed is 2 plus 0, which is 2. The corresponding hybridization mode is sp. Note that in our previous discussion on ethanol and ethane, we don't calculate the lone pair for C atoms. Here, we calculate the lone pair, but for C atom, it does not matter whether you calculate the lone pair or not because it is always 0.
Oh!
But for N and O, the number of lone pair is not 0 and you have to calculate it.
How to find the hybridization mode of O atom?
For O atom, like for N atom, you need to calculate the lone pair. For water, the number of sigma bond is 2. The number of lone pair is 2. The number of hybrid orbitals is the sum of the number of sigma bond and the number of lone pair, 2 plus 2, which is 4. And the hybridization from this key slide, which is valid for all elements, is sp3. For a non-ionic compound, the number of lone pair is always 2 for O atom. Example 7, CO2. The hybridization mode of O atom is sp2. The hybridization mode of C atom is sp. Note that these two atoms have different hybridization modes in the same compound, CO2. Here is the last example, example 8. Going through all the procedures, we can find the hybridization mode of carbon is sp2.
What is the relationship between hybridization mode and molecular geometry?
We will now look at the molecular geometry of all the 8 examples we have discussed just now. Now we summarize everything in this table. This is the relationship we get. We conclude that the geometry of the molecule depends on the hybridization mode of the central atom. This is a two-way relationship. Given the hybridization mode of the central atom, we can know the molecular geometry. On the other hand, given the molecular geometry, we can know the hybridization mode of the central atom. For these 6 compounds, given the molecular geometry, we can know the hybridization mode. For example, SO3 is trigonal planar, so the hybridization of the central atom sulfur is sp2. Beryllium hydride is a linear molecule, so we know that the hybridization of the central atom beryllium is sp. And the list goes on. The last thing I want to cover is pi bond. Look at this ethene molecule with sp2 hybridization. The carbon atom has one unhybridized atomic orbital, 2pz. This 2pz orbital will overlap with another similarly unhybridized 2pz orbital from another C atom. The overlapping of two 2pz orbitals results in the formation of one pi bond between the two C atoms. That's all my lecture for the day. I hope you enjoyed this video. Let me know in the comment section below if you have any questions. Also, subscribe to my channel if you want more of such animated education video from my channel. I'm Carl Tan. See you in my next video.